Hello, all. I welcome you all to the second part of the seventh lecture in EE 614. The last time, the last lecture, we had a discussion on diffusion and some constants like the diffusion constant dn and the ratio between the diffusion constant dn and the constant in the case of drift, that is mu n. And then we find that the ratio is a curious relation with dependence only on the temperature. It was an interesting fact, and then we stopped at that point. Now we will talk about a particular dynamics of carriers, which is called recombination and generation, which is very important in semiconductors, and this determines a lot of dynamics in carriers in addition to the drift and diffusion that we previously talked about. So now we will be dealing with recombination and generation, right? So let us take one by one and then see how they affect the carrier concentration and so on. So let us take, as we have previously seen, let us take a semiconductor, right, with some sort of a band structure. The bottom one is the valence and it's a conduction band, and let us say this is at some K, right? And at any temperature, there is some level of vacant states in the valence band, which is the density of holes, and there is some concentration of electrons. At 0 Kelvin, there are no electrons in the conduction band and all the valence band is filled for a semiconductor, right? Under this situation, the electrons in the valence band can actually, so we saw how the electrons in the conduction bands are filled, right? Because they form in pairs. The thermal energy is enough for it to excite from the valence band to the conduction band, and we know that the gap in the energy is Eg, called the energy gap, right, which is the smallest at this particular point, right? Now if an electron at the valence band having an energy E and wave vector k, these are the two things which determine at which point it is, right, has to be excited to the conduction band of energy E prime and k prime, right? They have to have this particular relationship where E prime is E plus some constant. So it can be h cross mu if the excitation happens from the valence band to the conduction band using an optical photon, or it can be h cross q in case they use what is called as lattice vibrations or phonons or whatever, right? This means that the energy is conserved as you move from valence band to the conduction band, and the summation should be equal to the final energy of the electron in the conduction band. In addition to the energy conservation, you should also have what is called as the wave vector conservation plus nu or q depending upon whatever it is, right? So nu is the wave vector of the photon and q is the wave vector of the phonon and so forth, right? So it is this wave vector conservation which determines how excitations can happen from valence band to the conduction, as well as the energy, of course. This relationship is what determines the optical conductivity, at which wavelength the semiconductor starts to absorb, which wavelength it is transparent and so forth. We will deal this particular aspect in the next lecture, but for now we will just say some very important observation, and then we will leave it for further details in the next lecture. The only thing being that, let us say that the wave vector in the of the electron, we know that k values range from 0 to 2 pi by a, right? And a being the lattice constant for silicon, we know it is about 5.64 angstrom, and this number tends to be somewhere around 10 power 8 to 9 centimeter inverse, right? Now if you take for example a photon, let us say a 532 nanometer photon, which has a k of about 18,736, and this, the k vector of the electron in the valence band is about 10 power 8, whereas the wave vector of the photon is about 10 power 3, 10 power 4 oddish, right? So the k prime, right, is about 10 power 8 to 9 plus about 10 power 3, which is approximately equal to 10 power 8 to 9, right? So what we are trying to say is your k and k prime should almost be equal if the excitation has to happen with an effect of, with a photon. That's why materials which have direct band gap, in the sense that the top of the valence band and the top of the conduction band are almost at the same k value. So this k is, let's say, k prime. Oh no, k prime is used. Let's say this is capital K, right? If the topmost of the valence and topmost of conduction band are at same k levels, it is only then they can be excited with a photon, because the wave vector of the photon is much small in comparison to the wave vector of the electron. This is called as an optical selection rule, right? That is why direct band gap semiconductors are very efficient when it comes to generation using a photon. So generation is a term when you excite an electron from the valence band to a conduction band, right? The same thing in the reverse case. So so basically generation is excitation from valence to conduction, right? Similarly, the opposite case is called recombination, which is conduction band to valence. The same sort of selection rules, that is, it should have an energy conservation as well as momentum conservation, holds if an electron from the conduction band comes down to a hole in the valence band. Now this can leave out a photon, right, or a phonon, depending upon the energy that is being involved here, right? The first process is called the generation. The second process is called as the recombination, right? For recombination, the recombination rate is actually a constant, let us say REC, times the number of electrons in the conduction band into the number of holes in the valence band, right? Because you need an electron in the conduction band as well as a hole in the valence band very close in k value to have the recombination to take place. Hence the rate is proportional to is equal to some constant times the number of electrons into number of holes in the semiconductor. The net recombination or generation, net dynamics in this case is written as U is R minus G, where R is the rate of the recombination and G is the rate of generation, right? So these are opposite phenomena. So the net transfer is R minus G, and at thermal equilibrium, you know that this should be equal to 0, which implies R should be equal to G, which should be equal to REC N into P, right? Which is what we saw before, and N into P at thermal equilibrium is actually Ni square, right? Now let us take a semiconductor, and which is, say, it's an N-type semiconductor, right, with a lot of electrons, such that N is equal to Nd, where Nd is a number of donor density that I have, and assuming that it is all ionized and so forth. This is standard assumption. And by some means, we will discuss about how you can do this. I'm going to disturb the equilibrium concentration. The equilibrium concentration is actually is described by the law of mass action, right? At thermal equilibrium, you always have N into P is equal to Ni square, right? And this is the equilibrium density of electrons, the relationship between the density of electrons and holes in any semiconductor material. And P in this case is Ni square by Nd is what we saw, right? I'm going to denote this by n naught and n p naught to denote that their equilibrium concentration, right? And for our current discussion, I'm going to change the density of electrons and holes as n equal to n naught plus delta n and p is equal to p naught plus delta p, where n naught and p naught are excess carrier densities that I'm going to inject either by means, let's say by means of a generation, right? I shine some light or put a thermal pulse or whatever that I have done, and I have changed this. And in an n-type semiconductor, you know that this is almost equal to n naught, because this n is so large and this small change that I have done is insignificant in comparison to this, so it is actually n naught, right? So the rate of recombination, as we have previously seen, is some constant into n into p, and which is equal to n naught into p naught plus del p, right? N naught is actually nd because it's an n-type semiconductor, so this is actually REC n naught p naught plus REC n naught del p. The net transfer under this situation where I have actually disturbed the equilibrium is R minus G, which is equal to REC Ni square plus REC n naught del p minus G is what we found to be REC Ni square, right? Again, so these two will go. The net rate is REC, n naught is nd del p, and this is typically written as del p by tau p, where tau p is 1 by REC nd. So the net change of carriers when in an n-type semiconductor actually depends on the carrier density nd and the small change in the whole concentration, the minority concentration, right? The minority concentration the minority concentration changes at the rate of tau p, which depends on the majority carrier density. If I rephrase this, let us I take an n-type semiconductor, right, with some density of electrons, and if I put some minority hole concentration del p in addition to p which was already there, this del p will change proportional to the density of the electrons that we have, the density of the majority carriers that we have. Higher the density of majority carriers, we see that this minority carriers recombine much quickly and then their carrier density drops down much faster, right? The same thing can be written for holes, for a p-type semiconductor as well, which can be written as U for, this is for n-type semiconductor, U for p-type semiconductor is del n by tau n, where tau n is 1 by REC n, right? So this treatment was is particularly for a semiconductor where we have a lot of direct or phonon assisted recombinations in the case, and which is more dominant when we have a direct band gap, right, where we have the electrons recombine without the assistance of any external species. The second kind of treatment is what we will do when the generation and recombination has some assistance, and the assistance is usually by what is called as traps. Assisted recombination or generation. So the previous treatment was the case in which the electrons and the holes recombine, or you have a generation of electron, or you have a creation of electron hole pair directly by means of a photon or by thermal generation. Now we have a treatment in which, let us say, we have some kind of an indirect semiconductor, right? You have holes and you have electrons, and they are separated by some by some k vector in which the direct generation and recombination are not as efficient as it was in the previous case. In these situations, you have what is called, or if you have a presence of what is called as traps. So this is called a trap site, which is typically formed if you have a defect, right, or you have an additional donor or an impurity. You take a normal semiconductor and you put an impurity such that it creates a state which is either empty in the general situation or it is filled with an electron, depending upon the kind of the impurity that you have added, right? And if this impurity has a state in the middle of the band gap, and let us consider a situation in which this guy is empty, right? You have an empty state in the general situation, then an electron which is present in the conduction band and you have a hole in the valence band gets trapped, right? Gets trapped in the trap site, forming an electron in the intermediate state, right, and creating a hole. Now this electron can recombine with the hole, because now that you have an intermediate step, it allows you to bridge for the gap in the k vector, right, and this will create an electron here, right. So the trap site which was in between, right, now it actually helped to annihilate an electron in the conduction band and a hole in the valence band, and it gets back to its original state. A second scenario is you have an electron in the trap state normally, right. In this case, if there is a hole in the valence band and an electron in the conduction band, right, now this hole in the valence band can recombine with the electron in the trap, right, forming an electron in the valence band, and the electron in the conduction band can fall down to the trap, forming a hole in the conduction band and the electron back in the trap site. Either ways, the trap site gets involved in electron hole annihilation, getting back to its original site, right? So it helps to bridge the gap or the separation in the valence and the conduction band, thereby aiding in this recombination process. So this is typically a two-step process in which the electron in the conduction band first needs to get trapped, and the hole in the valence band has to interact with the trap again to undergo this recombination. Hence, this particular trap assisted recombination process is actually a sort of a second order process. So it requires two independent activities. So we will handle each one of them separately, right? First, let us talk about the electron capture, right? So to know the rate of this trap assisted recombination, it has to undergo an electron capture as well as a hole capture to complete one full electron hole recombination, right? So the electron capture rate R1, right, is given, or it can be is actually proportional to the number of electrons in the conduction band, right, and the trap site, so 1 minus f of E of t is actually the probability that the trap site is at ET, right, at some energy ET. I have drawn here at the middle of the band gap. It does not necessarily have to be in the middle, right? It can be at any energy level in between. So the probability that this state is being empty is 1 minus f of t. That is when the electron can be captured in the trap site, right? And there is something called the trapping volume, or the let's say the electron in the conduction band should be in the proximity of the trap site, right? And that is given by Vt into Nt. Nt is the density of the traps that is present in the material, and Vt is the length that the electron travels in unit time, right? And that into the trapping density will give you the volume which is accessible to the electron, right? This product Vt into Nt is actually the density of traps which is accessible to the electron in unit time, which gives us the rate of electron capture, right? So Vt into time is actually the length, and that in 3 dimension will give you the volume, correct? Into sigma n is the capturing efficiency. So basically this is a constant of the proportionality, right? So basically the electron capture is proportional to the density of electrons, the probability that the state is empty, the cross section accessible to the electron, that is Vn into number of the trap density into sigma n. Now you have to also consider that the electron which is trapped can be re-emitted back to the conduction band, right? It does not have to undergo this recombination process with the hole, but can also be re-emitted back, thereby nullifying the initial trapping activity. So this R2, which is the actual trap emission, is proportional to the probability that it is the trap site is occupied, right, into the number of trap site and the emission probability, which is called as En. So this is again the constant of proportionality, and F is the probability that it is being occupied, right? So at steady state you have R1 is equal to R2, because at steady state there is no net change in the density of the trap site which is occupied, and the density of electrons in the conduction band, density of holes in valence band, nothing changes at steady state, right, at thermal equilibrium. So if this turns out to be true, then you have n into 1 minus f of e of t, Vn nt sigma n is f of e of t nt En, right? And En will turn out to be nt, you cancel, n into 1 minus f of e of t by f of e of t into Vn sigma n. And this, so basically you can write this as, I'm going to replace f of e of t as capital F, okay, 1 by capital F minus 1 Vn sigma n. So here we know that n can be written as ni e power ef minus ei by kt, right? And this is actually e power 1 by f minus 1 is actually et minus ef by kt Vn sigma n, which will finally turn out to be ni e power et minus ei by kt Vn sigma n. This is the electron emission efficiency, right? So basically this expression kind of tells us that the emission from the trap is very efficient if the trap is far away from the electron, from the middle of the band gap, right? So all we are trying to say is, in the diagram that we have drawn, if the trap site is, so basically this is ei, right, and the emission efficiency En is proportional to the exponential of Et minus Ei. So if Et minus Ei is let's say if Et is here very close to the conduction band, Et minus Ei is so far that the electron gets emitted back from the trapping site as soon as it gets trapped, right, and it stays longer in the trap site. That is, the emission efficiency from the trapped site to the conduction band is lower if Et minus Ei is actually very small, and that's what we mean by this sigma n, right? Now one can write the same expression for holes. So the hole, you know what, let's go to the hole a little later. At this point we will put it back in this expression, and we'll calculate the net trapping is actually R1 minus R2. R1 is the conduction band to the trap site efficiency, and R2 is the emission efficiency, right? So the net electron trapped transition is actually Vn sigma n nt n into 1 minus f of E of t minus ni e power et minus ei by kt, right? This is the net electron trapping efficiency. You can write it UN. You can calculate the same thing for holes, R3 minus R4, hole trapping. R3 is the hole trapping from the valence band to the trap site, and R4 is the hole emission from the trap site back to the valence band, right? Which will turn out to be Vp sigma p nt into p f of et, right? Because this is proportional to the trap site being occupied by the electron, because that's where you can actually that's the opposite of hole being sent there, right? Minus ni e power ei minus et by kt into 1 minus f of e. Right? This will be the rate for the hole trapping. Right? Now at equilibrium, again you know that un is equal to up, and if you equate both of them, you can actually come up with an expression for f of e of t, which will come out to be Vn sigma n plus Vp sigma p e power ei minus et by kt divided by Vn sigma n plus, you don't have to bother very much about, because these expressions will be given in the notes, of course. So basically these are long expressions. I might make some mistake, plus I'm just writing it down so that for our discussions it will be useful. Sigma p plus ni e power ei minus et. So we have an expression for f of t, and if we replace f of t in either one of these things, then we will know the net transition rate, because it has to be equal at steady state, right? Because the recombination, let me tell you why this un have to be equal to up, because neither each of the process can aid in an electron hole recombination. An electron hole recombination happens if an electron gets trapped from the conduction band to the valence band, and the electron moves from the trap site to the valence band, right? So only if un and up becomes equal, then you have a net electron hole recombination, which is assisted by the trap site, right? So if I put this one inside the any of this un and up, you will get the net rate as sigma n, sigma p. Sigma n and sigma p are the electron hole capturing efficiency, right? Vn nt pn minus n square, right? So you know this ni square. So ni is the intrinsic, and you know pn minus n square is how far it is away from the equilibrium, right? If pn is equal to ni square, then you have no recombination, correct? This should always be true for you to have any sort of recombination. This was true even in the direct band semiconductor case. Into sigma n plus ni e power et minus ei by kt plus sigma p plus Ni e power Ei minus Et by kT. So these two terms, right, they tell us that the recombination rate is efficient if the trap site is as far as possible, is as close as possible to the to the intrinsic site, right? Any deviation from this from the any deviation of the trap site energy from the intrinsic energy side will increase the denominator and hence will reduce the trap associated recombination rate, which is true for both electron and hole. So the main crux of this particular discussion is that the trap associated recombination is very effective if the trap site are deep levels or the trap site are close to the middle of the bandage, right? If it is close to any of the conduction band or valence band, then the emission efficiency becomes larger than the trapping efficiency, leading to reduced trap assisted recombination rate, right? So with this, let us say in the case if we have n type semiconductor where n is approximately equal to nd, then you can you see that you can, this one will reduce to sigma n, sigma p, vn, nt, p naught, del p naught by sigma n, which is del p naught by tau p, where tau p will turn out to be 1 by sigma p vn nt. So once again we have the trapping recombination lifetime inversely proportional to the density of the traps and inversely proportional to the trapping efficiency, of course, right? And the velocity of the electron. Velocity of the electron gives us, the product of the velocity and the trapping density actually gives us the trapping cross section, right? The same thing can be written for electron as well, which will turn out to be 1 by sigma n vn. This is actually vp nt, right? So this particular derivation is called as the Shockley Reed Hall recombination, and we have just seen how we can estimate the trap associated recombination rate if given the trapping density and the energy of the trap level. This is important because in many of the cases you can see that even a very small density of impurity which is added to the semiconductor can drastically reduce the lifetime of the minority carriers, which is very important for the p-n junction that we are going to discuss very soon, right? For instance, experimentally it was found that if you have even a ppm level of even ppm levels of AU gold in silicon can dramatically reduce the lifetime of a doping density of even just as small as 10 power 14 per centimeter. Right? So with these things we will stop now, and the next time we will meet, we will go and then discuss a little bit deeper on the optical properties of semiconductor. Okay, thank you.